And this is the AQA coursework NEA A-level testing video. My project is composed of two parts: a compiler from a high-level language with a design similar to C or Rust into machine code, and then a virtual machine that emulates the processor I designed and executes that machine code with a graphical output simulating the state of registers, memory, etc. For the first part, I'll be describing the instruction set for my computer and testing the assembler that converts the assembly language into machine code, the instruction set of the computer, and how this meets my objectives. I'll first describe it, how it works, and then talk about my objectives. So I've broken down the 13 different instructions into four kind of types, dictated by the first 2 bits of the opcode. The first one is a hold instruction whenever this encounters CPU execution stops. The second one is the R-type instruction, which combines all ALU operations, add, and, or subtract, into one instruction. These will have the same opcode. However, they're differentiated by the function field, which is a new field for this instruction format, which takes 4 bits and corresponds to the control bits for the ALU, which instruction is to be carried out. They all operate on 3 registers: a destination register and 2 source registers. Here's how they're encoded in the binary. First, the 2 source registers, and then finally the destination register. Each register is 5 bits because there's 32 registers in this computer, and the function field is 4. The next type of instruction are RI, immediate type instructions. These are the same arithmetic operations, but instead of being performed on 3 registers, they're performed on a destination register, a source register, and then a 16-bit immediate value. This partially helps make writing code a little bit easier because you don't have to load values into particular registers before you operate on them. You can operate directly on the values, but it also has some other advantages, which I'll describe a bit later. The next type of instruction with your prefix 10 are I-type instructions. These tend to work with memory and jumps. There's two types here: load word and store word instructions for the first 2, and then branch instructions later, conditional branches. To load a word from memory, there's 3 kind of components: a destination register, a source register, and an offset. The address you are reading from is calculated by adding the offset to the source register, and that value is fetched from memory and stored in the source register here. It's encoded with the source register first, the destination register, and then the offset, the numerical offset. The next 2 instructions are branch instructions, conditional branches. Unlike jumps, these work with offsets. You can have a positive or a negative offset, and that will increment or decrement the program counter to point to an instruction before or after the current one. It takes 2 registers. They're compared. If they're equal or not equal, depending on the instruction, the program counter is the offset is added to the program counter, which dictates which instruction is executed next. Jump instructions are a little bit different. They're completely unconditional, and they operate on absolute addresses. So you can jump to a specific address in memory that will always be the same. There's 3 types. There's a jump instruction, an unconditional jump that just jumps to an address, a jump and link instruction which jumps to an address specified by the 16-bit address field, and then stores the return address in the previous address of the program counter in a source register, and this can be used when calling functions to store a return address. And then finally, a jump register, JR instruction. This jumps to an address stored in a particular register in the computer. I'll look at evaluating this instruction set against my initial objectives of the project, showing that it meets all the requirements. The first objective is to use a RISC, a reduced instruction set computer architecture. This seeks to minimize the number of instructions an instruction set can implement to improve performance and efficiency, and I've cut this down into just 13 instructions. I've described a few workarounds I did to do this. For example, the function field here lets me combine all arithmetic operations into one, cutting 8 instructions out of the instruction set. The add immediate instruction means you don't require separate instructions to load values into registers or move values between them, cutting out 2 more instructions, and there's a few more that meet this objective. The next objective, 1.3, states that this instruction set should use 3 address operands, and that's exactly what this does. It has a destination and 2 source registers, or in the case of immediate values, a destination, a source, and a numerical value. This is the kind of standard assembly language format syntax that most programmers are familiar with meeting this objective. The next one, objective 1.4, branch and call instructions should calculate offsets from labels in the code. In this case, conditional branches operate on signed offsets, which are added to the program counter to jump to different places in memory, and the jump instructions branch to absolute addresses. These assembler calculates from labels placed within the source code, which I'll show you in a second. Objective 1.5 states that there should be macro instructions that can be used to perform common tasks, which reduce repeated code. In this case, for example, each stack operation and move and load instructions, they will have their own macros, which make it much easier to write in meeting this objective. Objective 1.6 states that I need a set of registers broad enough to minimize memory access. Here I have 31 registers, which is sufficient to avoid having to load and regularly load and store words from memory just to save space within the registers. And 1.7 states that the computer should have a word size of 16 bits, and in this case, all numerical values, all addresses, all values the ALU operates on, they're all 16 bits. Below here are the 4-bit function fields for the R-type instructions. So this 4-bit field, the different options are here. So if you wanted to represent an add instruction in binary, you would encode the opcode 0001, the 3 registers you want to operate upon, and then 0010, the 4-bit function field for a add instruction, and the same for all the others. The 32-bit registers are specified by 5 bits in the instruction set, and I've kind of written a default standard format for how to use these registers to the biggest effect. I always have the first register, the 0 register, always as a constant value 0. This can be used in conjunction with a lot of the other instructions to good effect. For example, if you want to load a value into a particular register, if you perform an add immediate instruction with the source register being 0, you can specify any 16-bit value and that will always be loaded into the source register. This means you don't have to have a specific loaded register value. You can cut down the instructions. The next 4 are arguments for functions. The next one is a return value for functions. Then there's 10 temporary registers, which are used to store kind of intermittent results in calculations, followed by 13 general purpose registers. I'd say they're used to store the equivalent of variables in programs. The next 2 are a base pointer and stack pointer. These are used to refer to the top and bottom of the stack. The compiler uses the base pointer to refer from offsets of local values on the stack frame. And then the last value is a return address. So whenever returning from a function, you always return by convention to the value stored in the return address. The final part of this instruction set is a few macro instructions that are defined. Because I sought to limit the number of instructions, it meant that there's a few instructions that aren't quite so nice to work with. So I wrote some macro instructions into my assembler. For example, pushing a register to the stack. This single instruction actually expands into 2 of these 13 base instructions that the computer can actually execute. The first one decrements the stack pointer, and the second one stores the particular register at that address, at the new address. The next 2, move and load immediate, are both aliases for the add immediate instruction. The first one here uses add immediate with a source and destination register. However, the immediate value is just 0. So you're adding 0 to the source register and storing that in the destination register, meaning you just move the source to the destination. Alternatively, the load immediate one instead sets the source register field to the constant 0 register. That's always 0, meaning the immediate itself is always loaded into the source register. The XOR instruction is a alias for 4 different and an OR operations and or a NOR. And just because it's quite a complex thing to write out, I wrote a macro instruction that can calculate the XOR of 2 numbers and store it in a destination. And the pop is the inverse of the push. It loads the value and then increments a stack pointer because the stack always grows downward. Or testing is to see that the assembler produces the desired machine code for a particular program. So I've got 3 different programs that I've hand compiled according to the instruction set I just described to show that the output is exactly what you'd expect. The first one is a program that just counts. You load a 15, you load a value into register R1. You increment the value in R0. And while R0 is less than R1, you repeat the loop. So you keep looping until it's run 15 times and R0 holds the same value as R1. So written down with the memory addresses, it's here. And this is the binary representation of each instruction. So if you see the opcode here, 0110 should correspond to add immediate, and here 0110. Same here with the 16-bit immediate field should be 15, and there you go, 15. Same with set of less than. So the R type should be 0001, the opcode 0001, and the function field, the 4 bits you'd expect to be SLT, so 0111, and here's 0111. A thing to note is with branch operations, the offset is relative. So in this case, you'd hope the assembler notices that this loop instruction, the loop label being referenced occurs 3 instructions prior, so the offset should be -3. And in 2's complement, it should look like that. So here is the binary representation of each instruction. Here is the hex, just converting that to hex. And the thing to note is that each instruction is 32 bits and the computer has 16-bit memory locations. So each memory location holds, each instruction corresponds to 2 consecutive memory locations. And I've used a thing called little endian encoding, which stores the least significant bits of an instruction before the most significant bits. So when these instructions are stored in memory, you'd expect them to be the opposite order to the way they are when they're actually compiled. So the FFF4 should occur before the B01B. So that's what you'd hope for, that there. And same here, CE001844, CE001844. These shows the assembler. You've got to show what I'm going to compile, test.out. This should test.asm. This should be the program just described a second ago. And to run this, I'll go run test.asm, asm out, test.out. So that's the compiled binary for each instruction, and you can see that corresponds exactly to what's on here. So 1011, 1011, 0110, 0110. So that's the binary representation of each instruction, and then to test the actual hex dump for the binary file it's produced. Here you go. This should be exactly the same as I've encoded in the hex. So FFF4 B01B, FFF4 B01B 003C 6044, 003C 6044. So you can see the assembler's outputting the correct machine code for this particular input. Next demo program is to show that jump instructions can calculate their offsets as an absolute value, and branches can do theirs relative. So looking at the 2 jump instructions in this program, you have jump to main and jump to double. So the assembler should look up the address in main, which should be address 6, and then double, which should be address 2. So when you compile these 2 instructions down, you'd hope that the a 16-bit immediate field is 6, and then 2 for the second one. And then when you compile that down into hex, this is the output you should be looking at if these instructions have all been compiled correctly as intended. So to show the output, so ASM double ASM, this is what I'll be compiling, the same program as here. So cargo run, there you go. And if you look quickly now, there's always 2 spare bits on the end, so you have to ignore those. The 16 bits here, that's 2, that's the address 2, and this one here is 6. That's 6 right there, 4 and 2. And you can see here the branch instructions are all 2's complement because they're negative values because it's an assigned value. And then if you hex dump this, the output is what you'd expect. So 0004, 6044. There you go. And FFF4 B043, FFF4 B043. So you can see that this program is being compiled as intended, and the jump instructions and branch instructions do correctly encode offsets and from labels, which is the requirement or objective 1.4. And the penultimate test I want to perform is showing that macro instructions work correctly. So the instruction I have here uses this stack to perform a few operations. So it loads value into the stack pointer, loads a value into R0, pushes R0 to the stack pointer, loads a new value into R0, moves that new value into R1, and retrieves the old value of R0 back into R0 from the stack. Then just performs an XOR. So this is what the program would write. Then the assembler should expand this into this here. So the push instruction becomes these 2 instructions, pop these 2, and XOR these 4. So that means when you compile it down, you should get a lot more than those 7 instructions. You should get this here, with all the expanded instructions are actually compiled down. So this is what you're expecting to get if this all functions correctly and they're being expanded correctly. So if I just show what I'm going to compile, it's called macros. Yeah, there you go. So that's the instruction, and then cargo run, ASM macros, out macros out. There you go. So you can see that's a lot more than 7. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you can see the number of instructions is being expanded correctly. So, and then if you do the hex dump, sam out macros dot out, you can see this hopefully should be the same thing, E000607A. Yeah, see that, and then C00131C, 131C. So you can see it's all expanding and compiling correctly. So macro instructions work, which is objective 1.5. Just to test the actual assembler itself, there's a few kind of key features it needs, right? It needs to handle the correct error checking, making sure the program is compiling if free of syntax errors. To demonstrate this, if you put in some unexpected character, say that's not handled by the assembler, and then attempt to compile it, test.asm out, test.out. It will point to a syntax error, and it will specify exactly where in the source code it occurred, the line and a little caret pointing to which character it is. Similarly, if you have an unexpected mnemonic, say, such as I don't know, BLT, an instruction I've not implemented, and you run that, it will see there's an unexpected mnemonic occurring, which doesn't exist in the instruction set. Furthermore, if you have a number that's, say, too large to represent, and attempt to compile that, it will have an integer overflow. It will say that we can't represent this in 16 bits and point to the number. And with registers, if you do a register that doesn't exist, it will say an unexpected register encountered. So you can see it checks the code for errors and refuses to compile it if it notices any. Actually, similarly, if you attempt to jump to a label that doesn't exist, like that, I believe this was 15, I think that was. Here you go. It will specify that you have not defined that label. Yeah, perfect.
Program is the virtual machine. This is responsible for simulating the process I just described and executing the machine code. Before I start, there is one thing I want to note. Objective 1.2, the computer must use a von Neumann architecture. It's difficult to show this properly, but here's the memory array used to store data instructions, and when programs are loaded into memory, they are loaded into the same memory that that data is also stored in. So you can see both instructions and data are stored in the same memory, and that meets that objective. Yes, the virtual machine, I'll run 2 of the programs we just compiled in the assembler, and then a further 2 programs to demonstrate the other functionality of the virtual machine. So starting with the first program we compiled, it's a program that counts to 15. While R0 is less than R1, it repeats all the code in the loop. Every time the loop is executed, R0 is incremented by 1. So this content in the loop here should be executed 15 times, and the final state of the program should hold R0 and R1 as 15. So to compile the program and then run it, here you see firstly the final state, both containing the number 15, and then these first 2 instructions here, the add are run, so 2 and 4, then 6, 8, and 10 after that, 6, 8, and 10. And you can see it enters a loop here, where 6, 8, and 10 are being repeatedly run. So if you count the numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So you can see the control flow works as the loop is being run 15 times, which is what you'd expect to see. I'll be running is the program we compiled second that effectively doubles the number in R1 10 times, or adds it to itself 10 times, meaning the result should be 2 to the power of 10 or 1024. On the right, I've got a few things to look out for to show this program is executing properly. First, after the first instruction, the PC should be replaced with 8 due to the jump instruction. And then after that, instruction 10 will execute and it will enter a loop that should run 10 times. The loop will be 12 and then it will call double, so 4, 6, return to 14, 16. And that should repeat 10 times while R0 is greater than 0. So the final state of the program should be RA, the return address, as 12, and then R0 as 0, since this is decremented every loop and it should run 10 times, and then R1 should store 1024. So to compile and run the program, here you are, you can see the final state. So the return address is 12, R1 is 1024, and R0 is 0. And then you look at the control flow here, you see 2, then it jumps to instruction 8, and then 10 executes, and then it runs into the loop we saw. So 12, 4, 6, 14, and 16. So that's the that's that, and that, which is what we expect. And they should run 10 times. So if you count the 16s, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then the program ends, hold. So the control flow here is working as expected as well. The program I'd like to execute is a little more complicated. It calculates the factorial of a number. Just to note that since the instruction set doesn't have the multiplication instruction, this here is one I've written. It adds the number in R0 to itself, R1 number of times. So if you're multiplying 6 times 4, R0 holds 6, R1 holds 4, and you calculate, in this loop here, 6 plus 6 plus 6 plus 6. The result is stored in V0, and the function returns to its calling location, stored in the return address. It handles stack allocation here, preserving the state of registers in the PC. Yeah, and then back to the main factorial function. So you call it by putting an argument here in the register A0. This loop here iterates that number of times as the number meant to calculate, so 7 times, and has a loop counter that's incremented by 1 each time, so 1, 2, 3, 4, 5, 6, and up to 7. Here, it multiplies the loop counter by the result each time, so 1 times 1 times 2 times 3 times 4 times 5 times 6 times 7. Yes, and then it returns the value in v0, the return address. This loop here is a break of greater than, so this here only terminates when R0 is greater than R2. So in the final state of the program, you should expect to see R0 is 8, because 1 greater than the parameter. So the final state of registers should look like this. You should have V0, the result being 5040, which is 7 factorial. R0 being 8, 1 greater than the argument, R2, 7. The return address should be 6 because that's 246, that's where it's being called from. And the program counter should hold to 8, the next instruction. So if you execute this, just compile it. And then run. Here you can see the final state. V0 is 5040. R0 is 8 as you expect. R2 is 7. The return address is 6, and the final program counter value is 8. So that's what you expected to see. Part to test about the virtual machine is its capability to display particular contents of memory as a graphical display. In this case, it uses the offsets from the address 0x8000 to store 128 by 128 pixel display. Each bit in a particular byte represents a pixel, so in total a row of 128 bits is represented by 16 bytes, and then 128 rows of those. So to set a particular bit or a number, you write a binary number to a particular offset from this base offset. So to set the first byte in memory, you have 0 offset, and since each row is 16 bytes long, to set the first byte on the third row, you offset it by 32, fifth row 64, etc. So when you execute this program, you should expect to see this number here written to the first address of VRAM, so the top left portion of the display. And due to the way binary works, this will be inverted, so you'd expect to see 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, where 1 represents a white pixel. Then it offset 2 rows, you expect to see a blank row, and followed by that a full byte written, 255, and then another blank row, and then a single 1 in the first location of that row. So to compile this down, and then execute it. Here you are, you get what you expect. The 0, 1, 0, 1, 0, 0, 1, 1, a free row, a full byte, a free row, and a single 1. So that's the output you expect to see. The reason this display stays open is because it's terminated by an infinite loop that keeps running and keeps the display open. I just want to note that because you're writing full bytes at a time, it's difficult to set an individual bit. To solve that, I use the XOR instruction to set a particular bit. You XOR effectively a bit mask for the bit you want to set, and that'll toggle that on or off, so you can use that to set a particular pixel on the screen. The second program I'm going to execute is one that uses a loop to fill the screen with a particular byte. In this case, it runs this loop 2048 times because that's the width of the screen times the height in bytes. So 16 bytes in a row times 128 rows, 2048. Each loop, it writes this particular number, an alternating number of zeros and ones, to to an address calculated by offsetting the byte you're on from the base address of VRAM, effectively writing it to the next set of pixels on the screen each iteration, and then it completes the loop counter once you've run it 2048 times, entering into a indefinite loop at the end to preserve the screen open. So to compile this down and then execute it, you should expect to see this here, an alternating pattern of zeros and ones the whole way through the screen as every single byte in VRAM is being replaced by this exact same number. Testing the virtual machine involves evaluating it against the two objectives I set myself. The first of those is that it should include a graphical display that shows the contents of VRAM. In this case, you can see there is a 128 by 128 pixel display that shows the 2048 memory locations after OX 8000, the first address of VRAM, and you can set pixels on the screen by writing bytes to memory. So that's that objective. The second objective states you need a toggleable debugger. So in this case, you have kind of two modes. You have the mode that shows the final state of the computer, all the registers and their values, and then you have a list of all the instructions the CPU executes, kind of showing the control flow of the program. This here, it has the opcode and then the various operands of each instruction. The final operand is interpreted either as a register or an immediate value, depending on the opcode. And by following this, you can kind of trace the execution of the program, and that's that objective met. Testing is to test the compiler. I'll first go through the process of creating and compiling a program, showing some error messages, and then I'll demonstrate some test programs that show the functionality of the compiler and the language itself. I'll start by writing a factorial function that takes in an integer parameter, returns an integer, and has a result, and returns a result at the end. I'll also note that if you have a incorrect keyword, say func instead of fn, and you try to compile the program, it should show an error there, expected fn or const, so if you try that, it will compile correctly. As you expect a main subroutine, so if you quickly include that, then call factorial with 6, say, and compile that compiles. But it also has type checking, so if you try to assign a value an incorrect type and run that, it shows you expected a different type. So to calculate the factorial, we'll have a for loop, I plus equals 1, and then result times the loop counter. So hopefully compiling that shouldn't produce any errors, and then it should produce this here. This is the assembly language that this is generated from the input, the program, and then compiling this here assembly down into machine code. SML factorial dot out produces this machine code, which is then executed by the virtual machine out. And there you can see that's the result of 6 factorial. And just to prove that's working, if you say change 6 to what, 5, say, compile that, and then run that, you get here 120, or 5 factorial. Second part of this testing program, I'm going to write a function, a program that uses variables, references, and pointers to kind of show how they work in the language. I'll start by creating a constant. The reference is a memory address, the first address VRAM, so I can neatly write to memory. I'll declare a main function, store some data, say, of an int type, just alternating zeros and ones. I'll have a while loop that keeps the display open, and then just for demonstration, I'll write the data to the address in VRAM, and this should just have a block there in the first address. Then I'll also write data to the address in VRAM plus 2, so 2 addresses over. So it shows how offsets work. There you go. Same data's been written twice. And now I'm going to write a function called modify. It'll take in a reference to an integer, return nothing, and all it will do is change the value of that integer to 255, say. So if you call modify with a reference to data, a pointer to data, then you execute this program, you should expect to see here. So the first thing it writes the zeros and ones, it then calls reference, and the second time it writes it, it now holds 255, or a full block. This is the binary representation of that number. To show this work with, say, not a reference, regular numbers, if you remove that, and then the reference, when you try to compile the program, it would still call reference, but because it's not passing a reference to the function, the actual value of data won't change, and it will write the same thing to both locations. Oh, and I'll also show another error message. If you say type the name wrong, and then attempt to compile it, it will show it's an attempt to call an undeclared function. That I need to show the language can do. For example, this is just a simple program that adds the number stored in A and 10, so you should expect 15 when you compile this, right? 15. If you, however, reference A, this section here will be the memory address of A, and because it's in 2's complement, when you perform this, you expect some negative number, because the memory address is around F000. So when represented in 2's complement, this should probably be negative instead of 15. Yeah, there you go. So minus 9, that's the result of the memory address of A, add 10. Similarly, if you store let B equals A, this should, and then do A plus B, this should return 10, I suppose. Oh, apologies. I forgot to write an equal sign. There you are, 10. However, if instead B is actually a pointer to A, and you attempt to add the 2, again, you'll get another negative number, because you're adding a memory address to 5. There you go, negative 14. However, if you dereference B, and you're pointing to the data stored within, that should be 10 again. There you go. And similarly, if you, after that, you store A to be 7, say, when you perform the operation, you'll see 14, because B points to A, and when A is changed, when you dereference B, it will also be changed. This program is a game of Pong I wrote in the language for this processor that will test the kind of capabilities of it all. I wouldn't describe in detail how it works, but you initially have the memory addresses of key regions in memory. You have VRAM, the delay timer used to time execution of the program to run at a regular frame rate, and then the keypad where particular keys set the bits in this byte. So if the up key is pressed, the first bit in the byte will be set, and you can check that every frame to determine which key is held down. There's 2 helper functions, mod and power, a few constants that I use to reference a player's height or the keys being held down. I wrote a set function that sets a particular pixel in memory to 1 or 0. It calculates an offset in bytes and then an offset in bits from that byte, and uses Boolean logic to set that particular bit. a rectangle function that uses that function to draw a rectangle. Every frame the draw function is called, which draws the 2-player paddles, the dotted line in the middle, and then the ball. And then back to the main function, you have a bunch of variables that store the kind of state of the program. It draws the border for the program. Every iteration, it sets the delay timer to be 1. Every 60th of a second, this delay timer is decremented in real time. So at the end of this execution, it waits until the delay timer is 0 to continue on the next cycle, because then you know that a 60th of a second has passed, 1 frame has passed, and you can run the loop again for the next frame. Each cycle, it draws the players and the balls, handles the input for the keypad, then updates the ball's positions and the velocities, and checks if it's out of bounds or collides with the paddle, adjusting the velocities accordingly. So to compile this program down into assembly language, there you go, code just to show what it looks like. In, out, main. This is the produced assembly code. It's nearly over 1,000 lines long. Here you are. And then compiling that down into machine code. It takes a little while, but here you go. This is the produced binary for the Pong program. And then executing that final Pong program here. You get an interactive game of Pong, where it bounces off the walls and your paddles, and you can use the up and down arrows to control your paddle. And this is all executing in the program I wrote, the assembler, and then the virtual machine that kind of shows the capabilities of the system. Just pointing out any particular things I forgot to mention about the language in here. You have constants here, references, return types of values, for loops, while loops, if statements with else clauses and else ifs, but I don't think any here an else if. You have combinatorial logic things. You have the ands or the ors with the double ands, dereferencing values in memory, binary logic. So it's a pretty complete language that can do many things. And as to how it meets the objectives I set for the program, here we are. So a standard syntax similar to C or Rust, I suppose, with semicolons and braces. That can be seen there. Statically typed language, yes, every time a variable is declared, it needs a type, and that type can't change through execution. It needs a procedural programming paradigm, yes. Programs are composed of functions with a main subroutine as well. It should support references and pointers. Yes, we've seen. There's plenty. There's up there. There's dereferencing, pointer arithmetic here with the offsets from VRAM. And it should produce error messages, as I've shown earlier. It even points out the locations of the error in source code.